All right, welcome back. And in this lecture, we'll take a look at other aromatic compounds, namely aromatic heterocyclic compounds and aromatic ions. So remember, if a compound can be aromatic, it will. And that means that we can change the orbital hybridization of lone pairs. So let's take a look at the following. Let's look at pyrrole. And we see here we have 2 4-pi electrons. Normally we would think, we've been trained to think of this lone pair as being in an sp3 orbital. So let me just draw my little orbital there. So let me say that normally we think of lone pair as being in an sp3 orbital, right? Because we have 4 things attached to the nitrogen. 1, 2, 3, and the lone pair is 4. But what if the lone pair was in a p orbital? So what if we had the following? What if we had our lone pair in our p orbital? Now we could go ahead and get our, I forgot an orbital here, sorry. Now we can go ahead and get our orbital overlap, because we've got 2 pi electrons, 4 pi electrons, and 6 pi electrons. So this would be 6 pi electrons. And that means that it would be aromatic. So again, because the aromatic compound is lower in energy, things are going to want to go towards their lowest energy state. So if we're debating, what's our hybridization here? Is it sp3? Well, that makes it non-aromatic. What if it's in a p orbital? And then these guys are sp2 here. So 2 pi electrons, 4, 6 pi electrons. It could be aromatic. So if it can be aromatic, it will be. And this means some other compounds like furan, thiopene, those are also aromatic, because one of those lone pairs could be in a p orbital. The other one would be in an sp2 orbital. You can't get both of those in p orbitals, because the other one would be perpendicular and wouldn't participate. What else could we have? Well, let's see here. We could have something like this. What if we had something like this? Well, now that lone pair is in an sp2 orbital, so it doesn't participate in our pi system. And we've got 2, 4, 6 pi electrons So that is aromatic. Let's maybe look at another one. Okay, so I'll draw my blob there. So that's going to be sp2. But what if we put this guy in a p orbital? Now we've got 2, 4, 6 pi electrons, and this is aromatic. All right, what if we had something like this? What if we had sorry, add in the hydrogens here. Now, these guys would be sp3. Why is that? Why not p? Well, if both of them were in p orbitals, we would have 2, 4, 6, 8 pi electrons. So instead, they're going to be sp3, and it's not a continuous, let me spell here, continuous. So that's going to be non-aromatic. So we've disrupted things by keeping those electrons in sp3 orbitals. Otherwise, if they were forced to be in p orbitals, we'd have, again, 2, 4, 6, 8 pi electrons, which should be anti-aromatic. Again, non-aromatic is lower in energy. If something can be non-aromatic instead of anti-aromatic, it will be. What about ions? The same actually works for ions as well. I'm going to draw in the hydrogens here just so we keep track of everything. Okay, so this is the cyclopentadiene ion, and this is aromatic, because this guy there that lone pair, I have a negative charge there, sorry, forgot about that, is that lone pair can be in a p orbital, so this would make this aromatic. And sometimes we actually draw this as the following. We'll draw it like so, with this sort of dash ring and a minus. Let's look at a different example here. And again, I'll put in the hydrogens for now, although on the practice problems and on the quiz, typically won't have the hydrogens. There's a negative charge. So that orbital there is going to be sp3. Now why is that? Well, if it was p, then we'd have 2, 4, 6, 8 pi electrons, which is no good. So, I mean, well, not no good, it means it would be anti-aromatic, but things don't want to be anti-aromatic. It would rather be non-aromatic. So this is non-aromatic. What if we had, instead of the anion, 1, 2, 3, 4, 5, 6, 7, we had the cation? What if we had this guy? Well, now, what's going on here? We have an empty p orbital. So what can happen with that empty p orbital? Well, with the empty p orbital, we can get that orbital overlap. And if everything is planar, we'll have an orbital overlap continuous ring of p orbitals, even though one of them is empty. That's fine. So we've got our 7 p orbitals here, and we have 2, 4, 6 pi electrons. So this is aromatic. In fact, we call this the tropylium cation, and it's pretty stable. And then again, sometimes it's drawn sort of analogous to our cyclopentadienyl cation. It's drawn like this. So you do want to get used to figuring out, so practice, get used to figuring out whether things are aromatic, non-aromatic, or anti-aromatic. And we'll go over more examples in class. All right. Let me think here if there's anything else I wanted to talk about. No, I think that's about it. So be on the lookout for aromatic heterocyclic compounds, aromatic ions, and of course the other aromatic hydrocarbons that we've seen already. All right. Well, hopefully you guys are getting a good grasp of aromaticity, and until next time, stay safe out there. Bye now.